Hello everyone, I'm Larry from Motion Software. Welcome to our second video on engine simulation technology. In this video, we'll focus on understanding cam specs and how to model camshafts. In the previous introduction video, we showed how DynoSim 6 simulates real-world dynamometer testing. We built up a high-performance Honda engine and provided some analysis of the results. If you didn't see that video, I suggest you give it a quick look. After viewing the introduction, you'll better understand how the simulation works in this video. We begin our in-depth look at camshaft timing by going over some of the essentials. While these concepts may be considered basic, they are fundamental to proper cam installation and entering cam specs into the simulation. Even seasoned engine builders can have issues with published cam specs, so we'll go over this carefully, step by step. When we reach the end of this video, my goal is that you'll feel confident with cam timing terminology and modeling. Issues with specialized cams will be covered in future videos. So let's see how a typical cam actuates the valves and how that motion is displayed in the simulation. In the world of automotive engines, valve actuation varies widely from a single cam to multiple cams in each cylinder head. If the engine uses a single cam, as shown here, the intake and exhaust lobes are driven on the same shaft. On multiple cam engines, there is typically one cam that actuates the intake valves and one for the exhaust valves on each cylinder head. Virtually all camshafts are driven by belts, chains, or gears at 1/2 crankshaft RPM. But regardless of cam configuration, the opening and closing movements of the intake and exhaust valves look quite similar. This display illustrates the up and down motion of the exhaust valves on the left and intake motion on the right. As mentioned, most valve motion curves have similar shapes. This is because they all must stay within the speeds and forces required to maintain reliability. Without careful control of valve motion, orchestrated almost entirely by the camshaft, valves and valve springs would not survive the billions of valve actuation cycles during the life of most engines. The intake and exhaust valve lift curves are depicted in this twin hump diagram, as shown here in Dynamation 6. In a running engine, valve events happen from left to right, within the 720-degree span of the four-stroke engine process. To highlight the details of valve motion, we first need to locate three piston positions, starting with bottom dead center, or BDC, on the power stroke, here. Then, the piston returns to top dead center, TDC, here, as the engine cycle switches from exhaust to intake. Next, the piston moves to BDC on the intake stroke. These points directly relate to camshaft valve event timing. Now, let's see exactly how valve timing points are measured in relation to TDC and BDC piston positions. First, notice that exhaust valve opening, called EVO, is shown here before bottom dead center, and exhaust valve closing, labeled EVC, occurs just after top dead center. Intake valve opening, called IVO, occurs just before TDC, and intake closing, IVC, occurs just after bottom dead center. These four valve events are all part of the camshaft primary valve timing specification. Now let's see how these timing points are entered into the simulation. Here, the intake valve opens at 40.5 crank degrees before the piston reaches top dead center, or BTDC. Intake valve closing falls at 76.5 crank degrees after bottom dead center, or ABDC. The exhaust valve opens at 89.5 crank degrees before bottom dead center, BBDC, and exhaust valve closing occurs at 37.5 crank degrees after top dead center, ATDC. So, primary valve event timing is defined in relation to piston and crank position. But what has not yet been defined is where on the valve lift curves these timing events occur. For example, if EVO is said to occur at 89.5 degrees before top dead center, how far must the valve lift off its seat for it to be considered open? This lift spec is called the valve timing lift height. Opening and closing lift heights are chosen by the cam manufacturer. Once applied, they lock the locations of the valve events to precise crankshaft and piston positions. Many cam manufacturers use the SAE, or Society of Automotive Engineers, standard of 6,000th inch valve rise to specify primary valve timing events. Even though the SAE standard was defined long before engine simulations were commonly used, the 6,000th inch lift height is also a good choice for cam timing analysis in simulations. This is because the SAE lift was meant to define the earliest point in valve lift at which meaningful flow can be measured, and that's exactly the lift point needed to calculate the start and end of mass flow through the engine, an essential requirement to simulating engine function and power output. The 4 timing points we have covered so far, plus the maximum lift of the intake and exhaust valves, complete the primary timing specifications for the camshaft. Now let's take a quick look at a cam card, also known as a cam tag, from Howard's Cams for a small block Chevy to identify these timing points. Event timing for primary lift points are commonly called advertised timing, as shown here. Many years ago, cam manufacturers used the large duration values calculated from advertised timing to promote their cams as bigger and better than the competition. That may seem a little silly today, but that's how they tried to outdo each other in the 1950s. Also based in the past, advertised valve timing nearly always translates to mean measured at the SAE standard lift of 6,000th inch valve rise. When a cam manufacturer uses other advertised lift heights, the values are almost always shown on the cam card. What is not always clear is whether the indicated lift height should be measured at the valve, that is, after lash and rocker ratio have been applied, or directly at the lifter. We'll delve into these details when we look at the next cam card in a couple of minutes. Next, let's see how these primary events and specifications are entered and displayed in the camshaft category in Dynamation 6. The primary timing points are shown here, and are 40.5 degrees for IVO, 76.5 for IVC, 89.5 for EVO, and 37.5 for EVC. Notice that after the primary timing points have been entered, the program is able to calculate the intake and exhaust center lines, the lobe center angle, and valve overlap. This is possible because these cam measurements are derived from primary timing points. Now let's enter the peak valve lift heights. The Howard's card shows a maximum valve lift for intake of 507 thousandths and 530 thousandths for the exhaust. These values are entered in the true lift at valve field. Then move up, select 0 for intake and exhaust lash, since this camshaft uses hydraulic lifters which generally adjust to 0 lash automatically. Finally, enter the standard small block Chevy rocker ratio of 1.5:1 for intake and exhaust valves. The simulation calculates and displays the lobe lifts from the entered values. To catch any errors, make sure they match the gross lift at cam values shown on the cam card. Virtually all cams are also supplied with a set of secondary timing points indicated on the cam card. Here they are labeled at 50 thousandths. I generally like the layout of this cam card because it clearly separates primary valve lift and timing from secondary lobe lift and timing. Secondary specifications are included to help engine builders accurately install the cam at the precise rotational position, called index, requested by the cam manufacturer. Here's how that works. As described earlier, the 6,000th inch SAE valve lift points mark when the valves just begin or just end meaningful lift. However, precisely measuring these low lift heights during cam installation can be difficult and can lead to index errors. To help eliminate these issues, secondary timing points are used. They are measured at 50,000th inch lifter rise when the lifter is moving much more quickly on the sides of the lobes. This makes it easier for the cam installer to accurately locate the timing points and precisely index the cam to the crankshaft. Secondary timing values were first published by Crane Cams and have become a well-established worldwide standard. It is important to know that secondary timing is based on lifter rise, not valve rise. This was chosen to minimize confusion since rocker ratios, valve lash, and valve train configurations are not involved in measurements using secondary timing. With almost no exception, 50,000th inch secondary timing is measured directly on the cam lifter or follower. Now let's transfer these secondary timing points to the simulation. Notice that all the cam lift and timing specs shown in the camshaft category have valve or lobe identifiers next to them. This lets you know at a glance when a timing event uses 6,000th inch valve or 50,000th inch lobe lift for its measurement. The 50,000th inch secondary timing is entered here: 13.5 for IVO, 49.5 for IVC, 62.5 for EVO, and 10.5 for EVC. After we enter secondary timing, the simulation has sufficient data to calculate the valve acceleration rates and gives an overall evaluation of camshaft dynamics shown by the color of these boxes. We also confirm that the intake and exhaust durations here match cam card specs. Here we see the valve durations on the twin hump diagram indicated with double-headed arrows. As you already know, primary valve duration is measured at 6,000th inch valve lift, and secondary lobe duration is measured at 50,000th inch lifter rise. Naturally, the secondary durations will always have a lower numerical value than the primary, since the secondary duration is measured further up the lift curves. The center points of the lobes, typically where valves reach their highest lift, mark out an angular distance in cam degrees between intake and exhaust lobes. This is called the lobe centerline angle, also known as the lobe center angle, LCA, or even the lobe separation angle, LSA. Take note that this value is the only cam timing measurement in cam degrees rather than crankshaft degrees. This is because LCA is not related to piston position or any other crankshaft timing event. Instead, LCA describes the rotational distance between the lobes as viewed on the cam itself. If the engine has a single cam, the LCA cannot be changed since it's ground into the cam when it's manufactured. When individual intake and exhaust camshafts are used, the LCA can be modified and tuned with adjustable cam sprockets or similar methods. Camshaft LCA degrees are simply 1/2 of the crankshaft degrees shown on the twin hump diagram. Also notice the intake centerline angle, called ICA, and the exhaust centerline angle, ECA. These timing durations are recorded in crankshaft degrees as they measure the rotational distances from the lobe centerlines to the piston at top dead center. Finally, the span of degrees during which both intake and exhaust valves are open is the overlap period, shown here. It is also measured in crankshaft degrees. Overall, I think the Howard's cam card does a good job of describing basic cam timing values. Here are a few improvements I'd like to see. 1. The advertised timing should specifically indicate SAE 6,000th inch valve lift. 2. The rocker ratios used to measure primary timing should be included. 3. 50,000th inch secondary lobe timing should be indicated as measured at lifter rise. Otherwise, this cam card is pretty complete and it's easy to model this cam in the simulation. Now that you're familiar with the basic cam card, let's enter the numbers and run an engine simulation using this CompCam's roller hydraulic profile, also for the small block Chevy. I've pre-built a basic engine minus cam data that we'll use for data entry. A good place to begin with all cam cards is to first enter specs related to valve lift, and start with lobe lift specs if possible. The lobe lift values are included on the cam card. We'll enter 330 thousandth inch lift for the intake and 335 thousandth inch on the exhaust side. Next is the rocker ratio. While it is not included on the cam card, we'll enter 1.5:1 for both the intake and exhaust rocker arms. This is the factory ratio, and this camshaft is designed for stock rockers. Since this is a hydraulic lifter camshaft, we'll set zero lash for both valves. The simulation calculates the true valve lift heights, and a quick check shows that they match the cam card. Next, we need to enter the valve timing for 6 thousandth inch and 50 thousandth inch lift heights. The cam card includes 6 thousandth inch timing, and we can enter 29 for IVO, 61 for IVC, 72 for EVO, and 24 for EVC. The simulation has now calculated the lobe centerline and the intake and exhaust centerlines. Unfortunately, the 50 thousandth inch valve timing points are not included on the cam card. This is very strange, since these are the timing points used to properly install the cam. Regardless, we can calculate the missing points from the data we already have. I'll open the Cam Math Calculator from the Tools menu. Since the center lines have already been determined, all we need to enter is the intake duration of 218 degrees, press Tab, and enter 224 for the exhaust. You'll see that the valve timing of 3, 35, 46, and -2 was calculated. Now we'll press the Apply to Secondary Timing button to transfer this data to the simulation. Now that all the cam timing specs have been entered, the simulation is completed. You can see these measured fields have been populated. They show the actual measured timing values used during the simulation process. In most cases, they will exactly match the desired values we entered previously. Okay, let's review how helpful this cam card was in building a simulation model. 1. This was an early CAMS card, and it did not include graphics or diagrams showing valve event timing. 2. The cam card indicated that the lift used during primary timing was 6 thousandth inch tappet rise. This, technically, is not the SAE standard of 6 thousandth inch valve rise. However, 6 thousandth inch tappet lift is equivalent to 9 thousandth inch valve lift because of the 1.5:1 rocker ratio and zero lash. Fortunately, the additional 3 thousandth inch lift won't introduce any substantive errors in modeling. 3. Finally, the comp card didn't mention that 50 thousandth inch secondary timing is measured at lifter rise. The bottom line is 50 thousandth inch valve timing was missing from the cam card, and it required some calculation on our part to complete the simulation model. Also, the SAE standard was not used. This seems to only make 2 to 3 horsepower difference, and it may not even show up in a real-world dyno test. In all fairness, this was an old cam card. As you'll see next, a more recently designed cam card from Comp offers an improved layout and additional cam data. Now let's use the information we've learned so far to analyze an additional cam card. This one presents its own challenges. This is a CAMSHAFTS.1 4055, a solid lifter design for the small block Chevy, typically used in street supercharged applications. It's a performance profile with a 3,000 to 6,500 RPM recommended power range. Because this is a solid lifter cam, it uses non-zero valve lash. To simplify cam installation, Comp selected an advertised primary timing lift of 20 thousandth inch lifter rise, since this checking height is not affected by valve train lash or rocker ratios. Now let's transfer the cam specs to the simulation and see if we run into any issues. As we did previously, we'll start off by entering the intake and exhaust lobe lift data. The intake lift is 362 thousandths and the exhaust is 376 thousandths. The rocker ratios are next, and again, they're not indicated on the cam card. But because the lobe lifts and valve lifts are both shown, we can easily calculate the rocker ratios by dividing the indicated valve lift by the lobe lift. In this case, the results are 1.49 for both intake and exhaust, which will round up to 1.5 to 1. Next, enter valve lash of 26 thousandths for the intake and 28 thousandths inch for the exhaust. The simulation now calculates the true lift at the valves, also called net lift. It's always a good idea to check these values with the cam card, and they do match once you subtract lash from the valve lift shown on the card. Next, we need to enter primary valve event timing. The cam card provides timing values measured at 20 thousandth inch lift arise, but as we've discovered, the simulation needs timing events at the SAE standard of 6 thousandth inch valve rise. How are we going to get past this hurdle? The easy way to solve this problem is to use another tool built into the simulation, the multi-standard calculator. It can convert one timing standard to another. Using the calculator is simple. Just enter the lift heights, the durations, and the conversion will be performed. Start by selecting 20 thousandth inch for the primary lift height and 50 thousandth inch for the secondary height. Then enter the duration values of 290 and 300 for 20 thousandth inch lift and 255 and 265 for 50 thousandth inch lift. Now press the Calculator Use button. The message box explains that the calculator needs the cam centerline values to complete lift height calculations. So we'll first enter 114 degrees for intake centerline from the cam card. However, the exhaust centerline was not included on the card. Fortunately, we can easily calculate it from the intake centerline and the lobe center angle, or lobe separation as it's referred to on the cam card. Use this formula, ECA equals 2 times LCA minus ICA. The result is 114 degrees. Notice that with centerline data, the multi-standard calculator is able to complete its SAE timing calculations. Press the Use button again to transfer the calculated timing to the simulation. With all values entered, the engine simulation is completed. Results are displayed on the right. Now let's review how well this cam card presented important cam installation and engine simulation data. 1. This Comp Cams card was well designed with good organization, but the valve timing graphics seemed incomplete. 2. Both lobe centerline angle and intake centerline were provided. 3. The cam card clearly indicated the lift height for primary timing at 20 thousandth inch, but it didn't indicate if this was a 20 thousandth inch valve lift or lifter rise measurement. I had to confirm that it was lifter rise in the Comp Cams catalog. 4. The maximum valve lift values were provided, but the cam card did not state that these values were measured at zero lash. And if it's your first time installing a solid lifter cam, this can be quite confusing. 5. Finally, the comp card provided secondary duration measured at 50 thousandth inch lift, but it didn't provide secondary valve timing or confirm that this was a lifter rise or valve rise measurement. I feel that this missing information should always be included on cam cards. When it's not provided, it's easy to understand why camshafts are installed incorrectly and poorly modeled in simulations. I hope this video helped you understand some of the standards, terms, and data made available by cam manufacturers. Please join me again next time when we continue our dive into cam cards and engine modeling. If you have a cam card that you would like to see modeled, send a clear photo or a PDF to support@motionsoftware.com and we'll share it in an upcoming video. and leave any questions or feedback you may have in the comments section below. Also, please like and subscribe to keep the tech information coming. We'll end with some invaluable advice from my friend Ferdy, who gained his insight from many years of building race-winning engines. See you next time.
Let's talk about over the head camshaft. Operate a cam follower, a bucket as we call it, or a rocker arm. On the follower, whatever action you will transfer to the valve has to be on the cam lobe. There is no other possibility. You want to increase the lift, you have to increase the lobe lift. And that's sometimes a hard thing to do. Now let's look at the rocker assembly. If you run a rocker off the cam, since you have a choice of ratios that you can run, 1.5, 1.6, 1.7, 1.8, the great advantage is you can reduce the lobe size on the camshaft. So that means usually less harmonics on it. Also the other advantage is if you use the rocker in the same amount of time or same amount of degree the camshaft makes, the rocker is able to open it quicker, faster because of the ratio. And that is an advantage, and that's why they went back to, in Formula 1s, to that again. And the other advantage is you have an open spring. If you need to, you could cool it very nicely. You know, let's say if you're on a motor up to 16,000, you can still run springs. Anything above that has to be pneumatic. But if you run springs, a valve spring will deteriorate very quickly if it starts to overheat. So if you need to, with the rocker, it's an open setup, you can cool the spring with an oil squirter very nicely. And that's also an advantage point. With the bucket type, usually it's half of the action is always shielded. So there's not much you can do with cooling the spring.